There's a lot of paper and card that we use that just never even enters the recycling stream. So labels, tissues, nappies. Even when paper and card is put into the recycling stream, a lot of it isn't recovered, and that's because it might be shredded, it's wet, it's contaminated with food waste. Mixed materials such as sandwich packs, envelopes, or plastic lined materials such as coffee cups, Tetra Pak, all of these materials would end up being rejected. At Fiberite, we're trying to achieve the end of waste. We've developed our core process, HydroCycle, which is able to take mixed residual waste and separate it out into the different material streams. We use water as a separation medium, so we're able to wash any organics off materials, we're able to separate fibers. We recover maybe 85 to 95% of that fiber. The VAMOS project stands for Value Added Materials from Organic Waste Sugars. We're taking residual waste fiber that we've recovered by the HydroCycle process and converting that through to high-value bio-based products for the circular economy. The fiber that we recovered, we combine that with enzymes in a reactor, and these enzymes are like mini scissors. They cut up the cellulose and they release the glucose sugars. These are industrial biotechnology sugars which can then be fermented or used as a chemical to make biofuels, biochemicals, biomaterials. Within VAMOS, we're using our sugars and they're being fermented into lactic acid.
Here at the Beacon Biorefining Centre of Excellence at Aberystwyth University, we focus on the production of high-value chemicals from a wide variety of biological feedstocks. Lactic acid is a platform chemical that can be generated from sugars by fermentation. Lactic acid fermentation from sugars is a process which has been undertaken for many years. However, usually the sugars come from food sources or are highly purified. We've been looking to isolate a bacteria that is capable of rapid growth and high-yielding lactic acid fermentation from the Fiberite-derived MSW sugars. The next stage of the process was to optimise the media and growth parameters for the strain to maximise lactic acid yield and minimise cost. We've conducted the fermentation at 1 and 10 litre scale, maintaining the same growth kinetics, productivity and lactic acid yield that we saw in our smaller lab scale experiments. Focus of the VAMOS project is to increase fermentation scale to 1,000 litres, which will be conducted at CPI's demonstration facility. Lactic acid is an important product used in the food, pharmaceutical and chemical industries. In addition to its other industrial uses, lactic acid can be used as a precursor for the biodegradable plastic polylactic acid, or PLA.
PLA, polylactic acid, is a bio-based biodegradable polymer. You can make PLA into packaging films, you can turn PLA into food containers, you can also turn PLA into textile fibers. Currently, PLA is made from sugars derived from corn or sugarcane. Making PLA out of waste material allows us potentially to lower the price of PLA, as well as move away from sugars derived from food crops. Here at the Department of Aeronautics of Imperial College London, we specialize on design and manufacturing advanced fiber composites for various engineering applications. In the VAMOS project, we take this PLA, we also take the fibers coming out from the Fiberite process, combining them to create waste pulp fiber reinforced PLA composites that can compete with polypropylene, polyethylene, or even glass fiber composites. We're exploring different composite architectures such as dispersing the fibers into PLA or creating a laminated construct to maximize performance. By incorporating waste pulp fibers into PLA, it allows us to create a more sustainable alternative to replace fossil-derived plastics. These materials could be used in applications where you want mechanical performance and biodegradability, for example in the agricultural industry, such as tree shelters, sheeting, netting and ties.
Lactic acid into PLA is just one of the pathways that we're exploring within VAMOS. We're also looking at using sugars as a chemical within resin formulations, as a binder, and fermenting it into different chemical products. The VAMOS project showcases the ability to take waste-derived fiber from the HydroCycle process and convert it into affordable and sustainable materials and chemicals.